Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Molecular Theory of Corresponding States. What is the principle of corresponding state is that defining a kind of a potential function which is suitable for all or which is applicable for all gases of a particular group or a particular class. That is what mean by principle of corresponding states. Then how to do this one, those kind of things we are going to see in detail. So, the principle of corresponding states purpose is to generalize treatment of intermolecular interaction that lead to non-ideal gas behavior. Let us say each non-ideal gas behavior whatever is there, that is being represented by some kind of intermolecular potential. That intermolecular potential may be including different types of forces, both repulsive and then attractive forces. So, can we have a kind of a generalization of this intermolecular potential for one particular group of non-ideal gases which are having similar nature, right. So, that is the purpose of this principle of corresponding states, and then that is what we are going to do. Okay. But before going into these principles of corresponding states theory, it is important to understand from molecular interactions viewpoint how different are these intermolecular potentials, right. So, in order to understand those things, we must have a kind of a kind of classification or classification of molecules from the molecular interactions viewpoint. So, then we can have something like a spherical molecules. For a particular molecule, if the intermolecular potential can be described by just two constants or two parameters, then we can say those molecules are more or less spherical molecules. For examples, molecules such as argon, krypton, xenon, these are considered as spherical molecules because their intermolecular potential can be described by using only two parameters. Okay. But there are a few molecules which are nearly spherical. They may not be completely spherical, they may be nearly spherical. Something like some non-polar or slightly polar molecules such as methane, oxygen, they are nearly simple molecules because they can be represented by these two parameter model, but there may be a kind of some deviation discrepancies as well. Then we have a non-spherical molecules which described by eccentric factor, right. So, let us say if the intermolecular potential of a particular gas cannot be described by two parameter models in general. So, then we can bring in another kind of parameter, third parameter, that we can call it as a kind of eccentric factor. This eccentric factor, if it is 0, then we can call those molecules are a kind of spherical molecules or simple molecules or spherically symmetric molecules. Okay. So, this principle of corresponding states is going to be different for simple spherical molecules and it is going to be different for non-spherical molecules, right. So, for both of them we are having different kind of approaches, those we are going to see anyway. Then also we can have molecules with permanent dipole moment, etc. Okay. So, now in other words, within one class the molecular interactions are similar. Let us say if the molecules, let us say if you take argon, krypton, xenon, these kind of molecules, if you take, they are more or less, they are spherical molecules. So, whatever the interactions that they are there in argon, they may be quite similar with the interactions that are present in the krypton molecules. So, how two argon molecules are interacting may be more or less similar to how two krypton molecules Kr interactions are there. So, that is possible, right. So, that is possible, that is what mean by classifying these molecules from the molecular interaction point of view. If the molecules are sphericals, let us say argon, so then whatever AR interactions like interactions are there, so they may be similar to krypton, that is Kr interactions. So, in such case it is also possible that AR and Kr interactions may also be similar. So, then we can group them together, we can put them in some one together group kind of thing, right. So, that is within one class, this class the molecular interactions are similar. If you have different types of non-spherical molecules, right, and then that non-sphericity is close to each other, then those molecules can also be kept as a kind of one particular group. Okay. So, further it has been observed that volumetric equation of state obeyed by all member of a class are similar. So, if the intermolecular potentials are quite similar to each other, then it is possible that their equations of state also quite similar to each other. Probably there may be slight difference in this constant, whatever the constant A and B constant that are present in equations of state, that is possible. But they would be similar if their molecules are of the similar nature. So, if the molecules are of similar nature, so then molecular interactions would also be similar nature. So, then their intermolecular potential functions would also be of similar nature. Then obviously, their equations of states are also going to be of a similar nature. In other words, if a given equation of state fits volumetric data for one member of a class, the same equation of state is likely to fit the data for other species in the same class, probably with different parametric constants. Let us say argon it is there. You fit the volumetric data PVT information of this argon information over a wide range of PVT conditions, then you have the data and then you try to curve fit that experimental data. Let us assume that for that argon gas you are able to fit well one particular equation of state. Let us call it that equation of state x. So, then it is also possible that the same equation of state x is going to be suitable for krypton and xenon as well, because these molecules are similar and their interactions are also similar to argon. So, that is what it is possible, but only thing that in that equation of state x, whatever it is suitable for these molecules, the constants may be slightly different from other. Okay. How can we put pictorially this similarity? So, let us say you take Lennard-Jones potential of a few gases, a few component and then compare. So, we will take a few non-polar molecules like O2, Cl2, C6, H6. If you observe their intermolecular potential divided by this K Boltzmann constant versus R, the intermolecular separation distance, then what will happen? This gamma by K is going to have a kind of temperature units, and then R is, let us take, if you, let's take in angstroms. Then if you take that experimental data, their PVT experimental data, and then if you measure their intermolecular potential with respect to different separation distance and then plot them in this form gamma by K versus R, then you can see for oxygen we have this plot, okay. For chlorine we have this plot, and then for benzene C6H6 we are having this part. So, you can see they are quite similar to each other. The only difference that you see here, this whatever the maximum attraction force or minus epsilon minimum, whatever the minimum potential function is there, that is different. Here it is something around 100, the ratio gamma by K ratio is for this case O2 case is roughly 100. For the other case for Cl2 it is roughly 450 to 500, and then for the case of C6H6 it is roughly 600, and their R minimum distance also different. So, here in this case it is small, in the case of oxygen, chlorine it is moderate, and then for benzene it is further still larger compared to the chlorine and oxygen. What does it mean? The C6H6 is having attractive forces for a longer range compared to the Cl2 and O2. That is what we can say this by this one, right? But they are quite similar. Only difference are these parameters are different. Okay. So, we can have a kind of generalized one, something having a generalized one like this, and then this may be having some kind of parameters which are functions of reduced temperature, reduced pressure, reduced molar volume, etc. Though that is what we are going to develop now. Not only for non-polar molecules, if you take a few polar molecules also in addition to these things, like if you take methanol and SO2 sulfur dioxide, then you can see this methanol is this one, and then this blue one is SO2 in addition to the other three, that is O2, Cl2, C6H6. Even they are also having similar nature. quite similar nature. Only thing that their this intermolecular according to intermolecular potential function, these minimum energies whatever are there, they are they are different compared to the other one, and then our minimum distances are different. So, having seen they are qualitatively graphically quite similar, they are looking quite similar. So, can we have a kind of generalized graph which is having similar nature, which is like this, but having some kind of adjustable parameters, and those adjustable parameters can be are a constant for any fluid, but one can obtain those constant A and B with certain kind of modifications. That is what the purpose of this principle of corresponding states. That is what we are going to do now. Okay. So, thus a number of different molecular species can be represented by a volumetric equation of state of same form as we have seen. In other words, it is possible to construct generalized correlations that is applicable to many different molecular species for both the equation of state and then density or pressure dependent contribution to enthalpy, entropy or thermodynamic properties. Then the ability to scale intermolecular interactions in this way leads to the principle of corresponding states, according to which what we can find out? We can find out dimensionless potential energy is the same for all species of a class, right. So, that is what we are going to derive. That is what we are going to derive. So, because we have seen this gamma by some function, let us say if I take another energy function, okay, rather than Boltzmann constant, then gamma by this is the intermolecular potential energy, and this is let us say I take let us say epsilon minimum, whatever the minimum potential energy that you get at the bottom. Let us say this is nothing but epsilon minimum. So, if this intermolecular potential, if you non-dimensionalize with this epsilon minimum, and then whatever this radial distance r is there, that if you non-dimensionalize with respect to sigma, sigma is let us say sigma is nothing but this distance where intermolecular potential is becoming 0 after overcoming the repulsive forces and then before starting the attractive forces, this particular point where it is gamma is becoming 0. Okay. So, any component you take and their intermolecular potential versus r you plot them, then you find out whatever epsilon by minimum and then that sigma, then you replot them by non-dimensionalizing this gamma by epsilon minimum and then separation distance r by sigma. Then you are going to get the same function, you are going to get the same function for all the components which are obeying this particular equation of state. Okay. That is what we call it as a kind of universal function, because now it is valid for all of them. And then first such generalized correlation arose from the study of van der Waals equation of state. So, what we do? We take the same van der Waals equation of state and then try to develop what is the generalized van der Waals equations of state. Okay. So, since we are trying to start with this one only, because this is the first work where principles of corresponding states have been developed, but it is not only specifically valid to the van der Waals equation of state, but it is valid for any equation of state. However, any equation of state with only 2 constant it is easy to get, but if you have more than 2 parameters as constant, then there is a kind of correction is required in terms of eccentric factor. Those things we will see in the later course. But let us start with van der Waals equation of state. So, let us say PV diagram of van der Waals equation, if you plot, let us say if you draw P versus volume curve for any component that is obeying van der Waals equation at different temperature, then you can have curves like this. If the temperature is less than the critical temperature, if the temperature is less than the critical temperature of that particular species, then what we are going to have? We are going to have the curve like this, where we can have a kind of a local minimum followed by a local maximum, right. The P versus V diagram if you plot for any van der Waals gas, at different temperatures, then we can get this such kind of curve. And if the temperature is less than the critical temperature of that particular gas, then we can have this PV curve like this, where we can have a local minimum followed by a local maximum. But at the temperature T greater than the critical temperature Tc, then if you plot this P versus V diagram, then we can have a curves like this, where you do not have any local minimum or local maximum kind of thing. Smoothly it is falling down, the pressure is smoothly decreasing as volume is increasing, right. So then what is about the case where the temperature is equals to critical temperature, right. If you have a kind of condition where temperature, operating temperature is equals to the critical temperature, and then you measure pressure versus volume information, and in that if you plot, you will have a curve like this, right, where the local minimum and the local maximum would be merging to the same point, where the local minimum and local maximum are merging to the same point, and then corresponding temperature is known as the critical temperature, and then corresponding volume is known as the critical volume, and then corresponding pressure is known as the critical pressure. That point is known as the critical point, or it is the point where the liquid can exist, that after that after that particular temperature liquid cannot exist. Okay. So, from this graph what we have seen, at T is less than Tc, that is critical temperature, there is a local minimum followed by a local maximum with increasing V over a part of specific PV range. Then at T greater than Tc, the structure of whatever the local minimum followed by local maximum is not going to be occurring, it is going to be vanished. But at T is equals to Tc, both local minimum and local maximum converge to a single point, and this point T, that is at T is equals to Ct, that is known as the critical point, the first and second derivatives of pressure with respect to V are 0. Obviously, for any curve, if you wanted to find out the maximum point, then what you do, you take the first derivative, right. Similarly, if you wanted to find out the minimum of any given curve, then what you have to do, you have to take the second derivative to be equals to 0. So, at this critical point, both the first derivative and second derivatives are going to be 0, because both of them are merging to the same point. This point is taken to be the critical point of the fluid, that is the point of highest temperature at which a liquid can exist. So, now we make use of this information, that is at particular temperature which is equal to the critical temperature, the P versus V diagram, in this curve we are going to have a one single point where both local minimum and local maximum are merging to the same point. That point we are calling as a kind of critical point. So, at this critical point, since minimum and maximum are merging to the same points, the first derivative as well as the second derivative of P with respect to V has to be 0 at T is equals to Tc or at the critical point. So, that information we make use and then try to develop a kind of information and then do some mathematical simplification to find out that generalized van der Waals equation of state, which is applicable for all gases which are obeying van der Waals equations of state. So, to identify the critical point for van der Waals fluid analytically, make use of these two derivatives at Pc and Vc, that is dou P by dou V at constant temperature should be 0 and dou square P by dou V square at constant temperature should also be 0, and then substitute in place of P, V, T, simply substitute Pc, Vc and Tc. Suffix C stands for critical point. Now, van der Waals equation we will take. Van der Waals equation is nothing but P is equals to RT by V minus B minus A by V square. Here you can see this A by V square. V is actually is having R power 3 form, right, because V is volume. So, then R is the distance. So, R cube power R power 3 terms kind of terms would be there. So, then A by V square in the sense something related to the A by R power 6. So, we have seen the attractive forces are inversely proportional to 6th power of separation distance. So, that means the second term in the RHS of this equation indicates the attractive forces, whereas the first part or the first term in the right hand side indicates something related to the repulsive forces, and this B is nothing but it is having similar like it is similar to like size of the molecules, or it is related to the size of the molecule. Okay. Now, for this equation what are we going to do? We are going to develop what is the generalized equation. Now, for a gas A, let us say if you take gas A, gas B, gas C and so on, so up to gas Z like that. All of them are obeying van der Waals equations of state, this equation of state. So, then for all of them A and B would be there, different values would be there like this. So, for each gas what is this small a, small b, that you have different values experimentally. Okay. But this is going to be valid, only thing that the nature of the curve is same, but only thing that these constants that are present in the curve are different. So, can we have a kind of one single curve where we can where all these equations can collapse to the same equation of state under certain conditions? That is what we are going to do. So, now that we can obtain when you apply these two conditions. At these conditions, now that is the local minimum, local maximum are there. So, this dou p by dou v at constant t is equals to 0 will provide us the local maximum point, and then dou square p by dou v square at constant t is equals to 0, this will provide the point at which the local minimum is existing. Okay. So, in fact they are existing at the same point if the condition is the critical condition, or if the temperature is equals to the critical temperature. Then let us do this dou p by dou v at constant t and then equate it to the 0, and then substitute in place of PVT simply substitute PC, VC, TC, because it is true only at the critical point. Okay. So, the differentiation of this equation we have to do. So, left hand side dou p by dou v is there, right hand side minus RT by V minus B whole square we get, plus 2A by V cube we should get, but now here this T, V etc. has to be replaced by TC, VC, and then dou p by dou v is nothing but 0. Similarly, dou square p by dou v square you do it, and then whatever the information that is expression that is coming, replace p v t by simply p c v c t c, and then equate this dou square p by dou v square to 0. So, that is now this equation whatever is there, if once again if you differentiate you will get dou square p by dou v square. Once again if you differentiate this equation by v, then you will get this equation. When you differentiate this equation once again with respect to v, then you will get plus 2 r T c by V c minus b whole cube minus 6a by V c power 4, because now T c now T and V are replaced by T c V c. So, now what we are having? We are having two equations and then two unknowns. So, let us find out these unknowns A and B and then substitute them here, because only these A and B are different from one gas to the other gas, that is obeying van der Waals equation of state. So, you find out this A and B as function of PCVC or PCTC or TC VC. In any two independent variables form you find out and then substitute here, you will get the one same equation, that is the generalized van der Waals equation of state. Okay. That if you do, so by solving equation 3 and 4. So, let us say equation 3 is nothing but 2a by Vc cube is equals to RTC by Vc minus b whole square. Now, this equation you multiply by 3 either side and then take whatever the Vc cube in the denominator in the left hand side to the right hand side. So, then this you have this equation, and then equation number 4 we are having this equation 6a by Vc power 4 is equals to 2 RTC by Vc minus b whole cube. Now, 6a you keep one side and all other terms you take to the other side. So, now these two equations if you divide one by other, left hand side you will have 1 and then remaining terms you will be getting 3 multiplied by Vc minus B divided by 2 Vc, that should be equals to 1. So, from here when you simplify this equation, what you get? You will get B is equals to Vc by 3. Now, you substitute this particular B in equation number 3, that is 2a by Vc cube is equals to RTC by Vc minus B whole square. So, in place of B you substitute Vc by 3 and then simplify, then you will get A is equals to 9 Vc RTC by 8. So, that is by solving equations 3 and 4 we get A is equals to this one, B is equals to this one. So, now substitute equations 5 and 6, that is constant A and B in equation 2, but at critical conditions. What is equation number 2? It is nothing but P is equals to RT by V minus B minus A by V square, but at critical conditions. So, now equation number 2 at critical conditions would be Pc is equals to RTC by Vc minus B minus A by Vc square. So, in that equation you substitute A and B, then you will get simply, when you simplify it, you will get RTC is equals to 8 by 3 Pc Vc R Pc Vc by RTC is equals to 3 by 8 is nothing but compressibility factor at critical conditions. Okay. So, why I am doing this simplification? Because if I wanted to represent this A and B in terms of PC or PC and TC or other PC and VC kind of terms, then it is required, this information is required, because now this A and B are in terms of VC and TC are independent as independent variables, right. So, now you take Vc is equals to 3b in this equation at critical conditions, right. Then you have, so Pc is equals to this RTC, in place of RTC you can write 8 by 3 Pc Vc, and 1 by, in place of Vc you take 3b, B is as it is minus A by Vc is nothing but 3b, so 9b square. Then you further simplify this equation, so that you will get Pc is equals to A by 27 b square. So, now you can make use of this condition as well as Pc Vc by RTC is equals to 3 by 8. Now, compressibility factor at critical point we will see, that is Zc is equals to Pc Vc by RTC, though we have already got it. So, Pc is not simply A by 27 b square, Vc is Vc RTC. So, this you rearrange, in place of A, equation number 5 we have already got A is equals to 9 by 8 Vc RTC, and then B and then this B square is let us keep as it is for the time being, right. So, then what we have, this Vc square, this Vc square, and then 9 by 8, this RTC is cancelled out, and then divided by 27, and then B is nothing but Vc. So, what we write? Vc square. So, now this Vc square is also cancelled out. So, that we have 9 1 ja, 9 3 ja, 3 1 ja, 3 3 ja. So, 3 by 8, the same thing we are getting the previous equations. So, now what we do? We convert this A and B constant in terms of temperature and pressure at critical conditions. That how you do? You simply write in this equation A and B, we have this equation already derived. In this equation, in place of Vc, you write 3 RTC by 8 Pc. Similarly, here in this equation B, that also we have got, here also in place of Vc, you write 3 RTC by 8 Pc. Then you will get A is equals to 27 R square Tc square by 64 Pc, whereas B you will get R Tc by 8 Pc. This is what you get. Now, here in this case A and B are represented in terms of Tc and Pc, and then similarly in terms of Pc and Vc, constants A and B are can also be obtained, but what you have to do in this equation, in place of RTC, what you write? You simply write 8 PC Vc by 3, then we have A is equals to 3 PC Vc square and then B is equals to Vc by 3 as it is. So, now these A and B constant here are in terms of PC and Vc. So, the same A and B constants are written in 3 different forms. First one is like TC Vc terms, second one TC PC terms, third one PC Vc terms. So, any one set, now we have 3 sets of A and B constants, any one set you substitute in equation number 2 then you substitute them in equation number 2 and simplify, then you will get generalized van der Waals equation of state. Indeed, that is what we are aimed to, finding out A and B constants and then substituting them in equation number 2. So, now what we do? We take this equation number 10, that is A is equals to 3 PC Vc square and B is equals to Vc by 3 and substitute them in equation number 2. We can substitute any other equations also, okay? Any other form of A and B also to get those generalized equation, but I am taking this one because of the simplicity. So, now this is the equation number 2, P is equals to RT by V minus B minus A by V square. So, P, whatever this A V square is there, I am taking to the left hand side, and then in place of A I have written 3 PC Vc square divided by V square, and then right hand side RT by V minus B is as it is, in place of B I have written Vc by 3. Now, both sides divide by PC. So, I have PC by PC plus 3 PC Vc square by PC V square is equals to 3 RT by PC, and then this term I have done the LCM. So, then we have this term V minus Vc by 3, I can write 3V minus Vc by 3. So, that 3 I have taken to the numerator. So, 3 RT by PC multiplied by 3V minus Vc. So, now this PC you can cancel out, okay, and then from this term next step what you do, you take a Vc common. So, when you take the Vc common, this term you can write 3 V by Vc minus 1, and then this Vc is multiplied by Pc. So, then that I can write RT by Pc Vc, 3 RT by Pc Vc in the right hand side term. Left hand side term is as it is, P by Pc plus 3 Vc square by V square, right. So, now what we can do here, this equation, this part 3 RT by PCVC is there. So, R by PCVC we can what is the value in terms of TC, that I can find out from this ZC information. ZC is equals to 3 by 8 is equals to PCVC by RTC. From here I can get PCVC by R is equals to 3 by 8 TC. Now, in place of this R by Vc Pc, if I substitute 8 by 3 Tc, then I can get this expression, 8 T by Tc I can have, and then this part I am taking to the left hand side here. Remaining term in the left hand side is as it is. Okay. So, what we have after substituting this A and B in this equation, we are having this expression like P by Pc plus 3 Vc by V whole square multiplied by 3 V by Vc minus 1 is equals to T by Tc. And we know this T by Tc is nothing but a reduced temperature, and P by Pc is nothing but reduced pressure, and then V by Vc is nothing but a reduced volume. So, that we define and then substitute in this equation, then we get PR plus 3 by VR square multiplied by 3 VR minus 1 is equals to 8 TR. The same thing I can write PR is equals to 8 TR by 3 VR minus 1 minus 3 VR square. This is the generalized van der Waals equation of state that we wanted to develop. Now, this is a universal function. So, how it is going to be? separate for each gas. Let us say if you wanted to obtain those A and B constant for separately for each quantity. So, you can use any of these constant that we develop in equation number 5, 6 and 9, 10. Then you can get those constant individual constant for individual gases. Okay. So, this is van der Waals equations in reduced variable or generalized van der Waals equation of state that we call. This form suggests that for all fluids that obey the van der Waals equation, Vr is same function of Tr and Pr, right. That is, at given Tr and Pr, all the van der Waals fluids will have the same numerical value of Vr. Okay. Fluids that have same Tr and Pr will have same Vr, and these fluids are said to be in corresponding states. Okay. So, now let us say this capital A, capital B, C and so on, so Z number of gases are obeying van der Waals equation of state. Okay. So, now these gases, each one of them are having different Tc, Pc, Vc values, obviously, right. So, for gas A, whatever Tc, Pc, Vc are there, they are different from the whatever the Tc, Pc, Vc. So, that way, so if they are different, so obviously their constants are also going to be different. So, but this information is clubbed such a way that now by using principle of corresponding states, if you write the same information rather than in individual temperature, pressure, individual volume kind of thing, you write them as a kind of a reduced temperature, reduced pressure, reduced volume. So, then that equation of state is going to have this same equation, this one same equation for all gases which are obeying van der Waals equation of state. That is what it mean by principle of corresponding states. So, that here this equation 12 can be called as a universal function for all gases that obey van der Waals potential. Okay. Thus, if the equation of state for any one fluid is written in reduced coordinates, that equation is also valid for any other fluid. So, that is, if potential function is made dimensionless by using some energy parameters, then this dimensionless potential is universal function of the dimensionless separation distance between the molecules. That is, as I mentioned, if the intermolecular potential, if you non-dimensionalize using minimum potential energy epsilon minimum, okay, then it is going to be one single universal function of a dimensionless separation distance r by sigma I for any gas that you take, okay, for any gas of one particular class, There are several classes of gases. Class in the sense, let us say for example, all the gases obeying Redlich-Kwong equation, you can put them as in one class like that for simplicity. Okay. So, why only it is function of reduced this separation distance or dimensionless separation distance, why not any other parameter? Because these potential energy functions we have seen, they are of form A by r power n minus B by r power m. This is A and B are positive constant and n is greater than m. This is what we have seen, generalized one, though it is looks like a Mies potential, but it is more generalized one, right, more generalized one for any gas which is having two constants. Okay. So, now here we can see these A and B are constants, only other independent variables is the separation distance. Okay. In some case it is inversely proportional to r, in some case it is inversely proportional to r square, in some case it is inversely proportional to r power 6, in some case it is inversely proportional to r power 8. I am not specifying whether it is electrostatic force or whether it is permanent dipole or whether it is induction forces or it is quadrupole interaction. I am not mentioning whatever the kind of force it is there, it is inversely proportional to r power something like n or m, something like that. That is the reason we are having only one dimensionless separation distance as a kind of independent variable if you are going to write this potential function as a kind of universal function. Okay. So, where epsilon I is the energy parameter used for scaling of potential function. In general, whatever epsilon minimum or minimum potential energy is there, that is in general used for a scaling, and then sigma is the distance parameter and characteristics of interaction between two molecules of species, and then in general for sigma I, people that is nothing but we take the r at which this gamma is becoming 0, that is taken as a sigma characteristic distance or collision diameter sometimes, or hard sphere diameter depending on the model, different names it is given. So, but mostly that collision diameter or whatever the sigma at which intermolecular potential becomes 0 after overcoming the repulsive forces and before developing the attractive forces. At that point where this gamma becomes 0, that separation distance is known as sigma. In some models it is called as a collision diameter, some model it is called as a hard sphere diameter, etc. like that. Okay. So, in other words, reduced potential energy gamma I by sigma I is same universal function of reduced distance r by sigma I. So, this is how we can develop a kind of reduced or generalized equation of state for a class of gases which are obeying same equation of state. Okay. And then finally, most importantly, it is valid for equations of state or equations of state whose intermolecular potential are having only two constants. Why? Because we have only two conditions. One is the dou p by dou v at constant t is equals to 0 and dou square p by dou v square at constant t is equals to 0, and substitute at Tc, Pc, Vc, that is at critical conditions. So, you take an equation of state and then do dou p by dou v, equate it to 0. Similarly, you do dou square p by dou v square, equate to 0, and then these two equations if you substitute Tc, Pc, Vc. So, we get only two equations. So, if these two equations having only two constants, maximum two constants, then only we can find out them. If any equation of state that is having more than two constants, then obviously it is not possible, because we have there will be three constants and we will be having only two equations to find out, that is not possible. Okay. So, but anyway there are some kind of corrections or adjustments are available that we are going to see anyway, but in general such kind of intermolecular potentials where we have more than two constants are in general non-spherical molecules. For those non-spherical molecules we can have a kind of additional factor omega p, which is also known as the eccentric factor. If it is 0, then we can say those molecules are spherical molecules. Okay. References for this lecture: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnit et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, and then Introduction to Chemical Engineering Thermodynamics by Smith et al. So, the lecture notes prepared for this lecture are primarily taken from these two books. Some information is also available in this book Koretsky as well. Thank you.